Good morning. My talk today is about a system for efficiently processing graphs that keep changing over time. Like Doug said, there are many use cases where you want to rerun algorithms on graph that keeps changing over time, and this is an attempt to do that. This is a joint work with many people, especially Chifan, Joey, and my advisor, Professor Ian Stoica. Before I get started, a little bit about me. Like Doug mentioned, I'm a PhD candidate at AMP/RISE Lab. I am looking at various aspects of this evolving graph as part of my thesis. Previously, I worked on a bunch of topics. My initial introduction to Spark was with a project called Carrot, where we were looking at collaborative energy diagnosis. And my mind was blown when I could do analysis on more than 300,000 devices in just less than 7 seconds, which used to take more than a day without Spark. Then I worked a bit on BlinkDB, which is approximate query processing, and lately I've been working on network analytics for cellular networks and looking more on trade-offs when applying machine learning to data sets that are coming in real time. Okay, back to the talk. So the main motivation for this work is that graphs are everywhere. For instance, here is a graph that many of us are familiar with. This is a graph of Twitter. It happens in P2P network. This is a graph of Nutella network. And in the internet, this is a graph which was as seen by Google at some time back. And in diverse domains such as biology and medicine, this is a graph of organisms and tuberculosis cells. Okay, so there is no doubt that there is plenty of interest in processing them, because it's not only that graphs are happening everywhere, it's also growing. For example, Forrester research indicates that almost 25% of enterprise graph databases would have data in form of graphs by 2017 end. So it's not surprising that there is a bunch of work both in academia and also in open source looking at processing graphs in a distributed fashion. We are all familiar with GraphX, which is an engine on top of Spark. Interestingly, there is an emerging new class of workloads that are graphs which change over time. Here is an example. This is activity of seismic sensors that are placed all over the world. Processing this data in a real-time fashion can be very useful. For instance, you can avoid disastrous situations and move people when there is an imminent earthquake. There are much more new scenarios which produce real-time graph data. For example, data from cellular networks are immensely useful for network operators if they can be processed in real time. For example, we have colleagues in Alcatel-Lucent and Bell Labs who are looking at how data is, how people are moving in cellular networks so that they can do better load balancing and so on. Not only that, there are many more emerging applications. For example, in Internet of Things, driverless vehicles, drones, and so on. Fraud detection is another example where this could be useful. We could also possibly perform what-if analysis on these graphs. For example, today in keynote, Iyer talked about a time machine, where if you could look at different states of your data, you could do useful stuff with it. It's very true in graphs too. If you could look at different states of how your network was, for instance, in cellular networks, you could do detection and diagnosis of problems. Hopefully, I have convinced you that evolving graph processing is an interesting use case, both from academia and also from the industry perspective. Unfortunately, none of the graph processing systems today support such workloads. So why is this case? We believe that this is because of two reasons. First of all, the canonical use case of graph processing systems have been in analyzing graphs that have been stored for a long time. Today we see more and more use cases where the graph keeps changing, like Doug mentioned. And secondly, there is also an interest in closing the feedback loop. So we want to make the analysis result and feedback into the system so that we could close the loop. So what can we do, and what are the challenges in making these systems or these open source graph processing systems support such workloads? There are three challenges. The first challenge is that of storage. How do we store evolving graphs over time? That's the first challenge. So the most straightforward way to do that is to imagine these evolving graphs as a series of sequential snapshots. So imagine here that the horizontal axis is time, and at different points in time, you see the graphs at different states. For example, at time 1, you see this graph. Some other point in time, you see the evolved graph, the graph has grown a little bit, and at a different instance in time, the graph has grown a bit more. So we have 3 graphs here at different points in time. Let's call them G1, G2, and G3. And we can store all these graphs, all the 3 graphs in the system, and then process these snapshots one by one or in parallel to achieve what we want. But the problem here is that storing these snapshots results in a lot of storage overhead. That's because most of the graph here did not change. The 3 nodes A, B, and C remains the same across all these snapshots. So if you are storing these graphs separately, you end up storing these multiple times, and hence you incur a lot of storage overhead. So the second overhead is that of computation. So imagine that you want to do some computations on the graph that you have stored, and imagine that you are storing multiple graphs to do this evolving graph processing. So again, the same example, you start with graph 1 and you are applying an algorithm on the graph when it's available, and you end up with a result which is shown as R1 here. Now you get a new graph which is G2, and what you will end up doing is you will restart the computation on the graph and end up with result R2, and so on. The problem with this approach is that you are wasting computation. You are doing the same computation again on the second snapshot and again on the third snapshot, thus wasting computations. The third challenge is that of communication. So all the distributed graph processing systems today do computations by exchanging messages between entities of the graph. In the previous example, when we were doing computations on the graph, the framework does that by making graph entities exchange messages. Hence, in this case, performing the same computation again and again exchanges the same messages between the entities, thus resulting in a lot of messages being exchanged that are redundant. So in this project, we are looking at how do we process time evolving or dynamically changing graphs efficiently. And the answer to our question is that we can do this by sharing the computation, communication, and the storage. We have implemented these techniques that I'm going to talk about in the next few slides in a system called Tegra, and I'll start with the storage optimizations that we make. So coming back to our original example, storing snapshots is expensive, that like I talked about. So one potential solution is to just store the differences between the graphs. For example, here we'll store, when the first snapshot is available, we are going to store the entire graph. When the next snapshot comes in, we only want to store the difference between the first graph and the second graph. In this case, it's a new entity D and the edge between A and D. And when the third snapshot comes in, we do the same, the difference between the graph G3 and G2, and so on. This is an approach which is taken by many systems, especially in storage systems and also for backup systems. But there is a problem with this approach when you try to apply this into graph settings. The problem is that when you want to do some computation on the graph, you have to reconstruct the entire graph. And reconstructing the graph in systems like Spark or dataflow systems can be expensive. Imagine that there are thousands or 10,000s of deltas in the system and you want to recreate the graph, it could be expensive. So the solution that we propose in Tegra is to adopt a persistent data structure. Just a quick look at persistent data structure for those who are not familiar. The key idea here is to preserve an old version of the data set when you mutate the data set, so that you have access to the old version and also the new version, but lends nicely to the immutability semantics by many big data frameworks. Here is an example. So this is a tree data structure which stores data at the leaves, and the keys are the nodes here. Suppose that at time t1, you have a data set which is indexed by the tree, and you want to mutate one of the leaves. So what a persistent data structure allows you to do is just copy the part of the data set that changed but share the structure with the rest of the data. So here you have a new version T2 which shares most of the structure with the earlier data set. So we leverage part, which is data structure that was proposed by the indexed RDD work that came out of AmpLab recently, and we modify that to work with graphs. Specifically, what we do is this: we create a graph snapshot index, which consists of multiple partitions. The graph is obviously partitioned into multiple machines, and in each of these machines we create two part trees, one for the vertices and one for the edges, and then we coordinate the snapshot generation using a snapshot ID management system. This enables us to share the graph without any of the storage overheads, but also gives us immediate access to any of the snapshot without the overhead of creating the graph snapshot from all the deltas like I talked about earlier. Okay, let me talk a little bit about how Tegra optimizes communication overheads that I talked about earlier. So before that, I want to spend a bit of time explaining how these frameworks process graphs. Most of the existing graph parallel frameworks adopt a vertex-centric computation. This is what I mean by a vertex-centric computation. As a developer, you are only interested in writing a vertex program. So at any point, you are looking at one vertex, and you write a program that does three things in a model which is very popular called GAS model. So in GAS, the developer writes three functions to execute on every vertex of the graph. The first one is a gather function, which gathers all the neighborhood information. The second function is an apply function, which applies the gathered information to update the value of the vertex under consideration. And finally, there is a scatter function, which scatters the updated value from the vertex to all its neighborhood. The gather and the scatter phases are implemented using exchange of messages. Okay, with that in mind, let us imagine applying a graph algorithm on multiple snapshots simultaneously. For instance, this may be a data analyst who is interested in learning how a social network evolved over time, or it might be a network operator who is looking at different snapshots of the network and trying to figure out what changed in the network. So the strawman approach is to apply the graph parallel algorithm independently. You will have an outer for loop which is iterating over the snapshots, and the inner for loop which does the GAS computation over the snapshot, which means you will end up doing the computation again and again and end up sending the same messages like we saw earlier. So in Tegra, we propose a very simple solution to solve this. Instead of considering the graph snapshots independently, what we do is we look at them as applying the graph parallel algorithm on each. Instead of applying the graph parallel algorithm on each of the snapshot, we apply each stage of the algorithm to all of the snapshots. For those who are familiar with database concepts, this is just flipping of the loop. So instead of the outer loop being the snapshots, we just take the loop to the inner inner loop. And what happens is we can consider all the snapshots as one, and each of the stage can now independently work on all the snapshots, which means it doesn't have to send the same message again and again, and it doesn't have to do the same gather, apply, and scatter computation if the vertex or edge did not change over time. Although I talked about sharing communication, this also results in reduction in computation because you are also doing the apply function over the entire snapshot, which means you don't have to do redundant computations. This results in a lot of reduction in both computation and communication, and it can be much better when the graph is large. So finally, let me talk a bit about computation optimizations in Tegra. So in our earlier example, we imagine that all the snapshots are available for us to work on at the same time. This may not be the case. For example, in the example that Doug mentioned, you have a streaming graph and snapshots are being formed all the time. So when you have access to a snapshot, you don't have access to the next snapshot at the same time. So what do you do then? Specifically, if you have results from running your algorithm on an earlier snapshot, how can you reuse them? So in the literature, there has been 3 approaches to tackle this problem. The first one obviously is to restart your computation on the new snapshot. But as we saw, this results in a lot of redundant computations. The second approach is to do memoization. For example, there is a research prototype called GraphInc, and what it does is to keep track of all the messages and all the states of every graph entity over time, and it figures out which part of these has changed, and then it can reuse parts of the graph that did not change. The problem with this is that if you look at even a moderately sized graph, the amount of messages and the state in such a system is huge, and this results in a lot of storage overhead and also fault tolerance problems. Finally, there is approaches which use operator-wise state. For example, in IAT, what it does is it incorporates operators that are incremental, which means every operator keeps state, and if you can express your graph computation in terms of these incremental operators, then you can achieve incremental computation. But the problem here is that as a developer, you are left with how you want to implement your graph algorithm, and if you implement it in a not optimized way, it results in a lot of overhead. And there is also this problem of keeping state at these operators, which results in bad fault tolerance. Okay, the key idea that we have in Tegra is to leverage how the gas model executes computation. So we know that each iteration in gas modifies the graph by a small amount. And what this enables us to do is to look at the computation also as an evolving graph. So not only across time dimension, we can also look across iteration dimension and see the iteration evolution as another evolving graph. And we can store this, we know how to store this efficiently in Tegra, and we can reuse the stored iterative evolution to our advantage when the graph changes. Specifically, when a graph changes, we can mark parts of the graph that changed, then expand the graph to also involve regions for recomputation, and then borrow parts of the graph that did not change at all. I'll walk you through an example of what I mean by this. Imagine that this is the time dimension, and we have a graph available at time t1, and we are doing computations on this graph. Imagine that we are doing connected components computation on this graph, which means the entities exchange messages, and in this case, the component ID happens to be the smallest vertex ID. So after 2 iterations, after exchanging messages between the entities, the connected component is formed, and all the vertices end up with the same component ID. Now, in Tegra, what we do is we store this evolution also as a time evolving graph. So we do not only store G1, we also store G1 first iteration and also the second iteration. Now when a new graph is available, what we can do is we can look at the difference between the corresponding iterations. So we look at this particular new snapshot and the first and the 0th iteration of graph 1, and we see that the only change here is the new entity D and the edge between A and D. But it's not enough if you just do the recomputation on D, because in graph computation using gas, the neighborhood also changes. So if you just end up doing computations on D, you cannot accommodate any graph deletions on graph changes. You can only accommodate graph additions. But we also want to accommodate for deletions and changes to graph entities. So what we do is we expand the area of recomputation by leveraging how gas does computation. So in this case, since A depends on D, we also mark A to be recomputed. But B and C can remain the same because they are not in the immediate neighborhood of the entity that changed. So we can reuse results from the old one. So in this case, only A and D exchange messages, and we can reduce the exchange between B and C. And in the next iteration, we do the same. We can look at the difference between the first iteration of the previous snapshot and borrow the values that did not change, and so on. In this case, the reduction in the messages exchanged and computation may not be significant from this very simple toy example, but in larger graphs we have seen that this results in a lot of improvements both in terms of message exchanges and also the reduction in computation. Okay, just a little bit on the API that we have right now. We have implemented this on top of Spark components graphics and graph frames. I'll highlight a few of the important changes that we have made. The first change is we support the persistent data structure as the backing for all the graph snapshots. In graph frames, the original data is stored in data frames. So we expanded data frames to have an indexed backing where the data is stored in part structures instead of the normal RDD compressed data structure. And once we have this indexed data frames that are being used in graph frames, we can do updates to the graph using the new update API. To do incremental computations, we expanded all the existing graph algorithms in graphics and graph frames. For example, here we have a graph created from the vertex and edge data frames, and you have run a computation. For instance, here you are running triangle count, and when you want to update the graph, you could just call update on the graph and then rerun the computation by passing in the old result that you have, and it will use our optimizations that I talked about and not do any redundant computations. Finally, we can also work on multiple snapshots of the graph. For example, suppose you have 3 snapshots, G1, G2, and G3, you could do the same triangle count on multiple snapshots by calling run on snapshots instead of just calling on single snapshots. Note here that the result data structure that you get back contains 3 results for all the snapshots, and its sharing structure due to our storage format. We have expanded the graphics API also to make this work by considering the snapshot ID in all the operators in graphics, and we are working towards integrating this with more catalyst optimizations. Okay, I want to briefly talk about preliminary evaluations that we have done on Tegra and see how it works. We have expanded, we have tried it on 2 data sets that are available as open source, the Twitter data set and also the UK web data set. The first experiment that I am showing here is showing the benefits of sharing the storage on increasing number of snapshots in the system. So in the x-axis, I have the number of snapshots that the system is storing, and the y-axis is the storage reduction. So right now I am only showing the storage overhead by graphics or graph frames, and this is the storage reduction is compared to graphics or graph frames. We see that the more graph snapshots that we have in the system, the storage overhead reduction is more significant. There is a small caveat with using the part data structure, in that when you have very small number of snapshots, the storage overhead is a little bit more, but we are actively working towards optimizing this. The second graph here shows the benefits of sharing communication. Here again I am showing the number of snapshots in the x-axis and the time to compute a graph algorithm on all these snapshots simultaneously on the y-axis. And this is a comparison between vanilla graphics or graph frames compared to Tegra. And we see that the reduction in computation time is significant with larger number of snapshots. Finally, this is the benefit of incremental computation. What we do here is we take the Twitter graph, and in every snapshot we are changing 1% of the graph. We start with the original graph, we compute the connected components on the graph, and after changing the graph by 1%, how much time does it take for Tegra to complete the computation compared to restarting the computation. The orange line on the top shows the recomputation time, and the blue line shows the recomputation time by Tegra, which is much more significant, and we see up to 50x reduction in computation time because it's only working on the modified part of the graph. So to talk a bit on the ongoing work and future work, we are working on more tighter integration with Catalyst, especially we are looking at tungsten improvements, because right now we are not taking advantage of all the tungsten improvements because we use our own data structure. We are working towards creating a Jira for code release. And as part of future work, there are a lot of things that we want to look at, especially more pressing need is incremental pattern matching. For instance, you want to find fraud detection in evolving graphs. An exciting area is to look at approximate computations on evolving graphs. What if you don't want the exact answer? Can you speed up computation a lot by providing an approximate answer? And finally, all these data that I talked about are inherently geo-distributed. They are produced at multiple locations in the world. So can you do computations at those locations rather than bringing the entire graph to a centralized location? To summarize, I've talked about time evolving graph processing and how it can be useful. And we proposed a system, Tegra, that solves this problem by sharing storage, computation, and communication. Please come and talk to me about your interesting use case. We are always interested in getting your inputs and improving our system. With that, I'll stop and take questions.
So we have time for one, maybe two questions. You look really excited here, so no pressure.
Thank you. Yeah, great talk. And I've been using graph frames a lot for computing a bunch of stuff on with Python, but still great tool, and I'm excited about this extension. But one question I have is that you are trying with this tool to reduce the amount of, let's say, messages or computation as you have more snapshot. But I'm not sure if maybe you can expand a little bit on how your approach makes those reductions without actually running the algorithm, because I feel like you need to run the algorithm to know what are the messages that are going to be exchanged. You need to do it anyway. So.
Okay, good question. So all the benefits come when you have the result computed initially. So I talked about two scenarios where you have the all the snapshots available at the same time and all the snapshots not available at the same time. So it's imagining that you have computed at least once. So when you have access to the snapshot initially, you run the computation. There we don't provide any benefits at all because you have to do the computation anyway. When a new snapshot comes in, rather than restarting, we store all the things that happened with the earlier snapshot. That is one way. The second way is you look at multiple snapshots and you want to do the same computation on all the snapshots. In that case, you can reduce the messages by combining all the snapshots and looking at all the snapshots on each of the gas stages, rather than looking at across the different snapshots, right? In that case, you can generate the same message and apply it to all the snapshots at the same time, rather than generating 3 messages, for example, in 3 snapshots.
So we have 30 seconds here. Who has a really short question? Okay, we'll go here.
So you had on your future works to open source the code, or is it a part of Spark 2.0 right now, or?
It's not a part of Spark right now because it's built on top of graph frames, and graph frames is not yet part of Spark. So we plan to release this as open source. I don't know what's the plan, if there is a plan to integrate this with Spark at all.
Okay, but regardless, there's a plan to release this as a standalone open source thing that then built on Spark, right?
Right. Yeah, it's built on Spark and graph frames, yes.
Okay, great.
All right, thank you very much. Excellent talk. Really glad to have you.
Thank you.